After our discussions on energy eigenvalues, it's time for us to now obtain the energy eigenfunction and complete the problem. So during the derivation of the energy eigenvalues, we obtained the relation 2n plus 1 minus lambda equals 0. This means that lambda equals 2n plus 1. Now this implies lambda minus 1 equals 2n plus 1. Now you can substitute this 2n plus 1 for lambda minus 1 back in your equation 8, and your equation 8 would read t square hn of y by dx square minus 2y dhn of y divided by dy plus 2n hn y, which is equal to 0. This is still of the form of Harmonic polynomial, Harmonic differential equation. Therefore, the solution will be the same, the asymptotic solution that we assumed earlier. The only thing is that that solution is not normalized. The asymptotic solution, as we know, is psi equals h and y exponential minus y square by 2. This is the asymptotic solution. Now we have to normalize this to finish the process. So we have to add first a normalization constant with the suffix n next to it, and the condition for normalization is integral psi star psi dx. See, here it is dx, and you have your psi in y. Why the probability is calculated in dx? That's a question that need to be answered, because dx is your real space. Dx is directly gives you the extent to which you have stretched and released your harmonic oscillator, the extent to which it has been displaced. And y is only a scaled version of that. Y is some constant into x. So the probability has to be calculated in the along x. So dx has to be added here, and this has to be replaced by y, which we can do if we know the relationship between x and y. We know that y equals m omega by h cross the whole raised to x. And therefore dy or dx will be h cross by m omega the whole raised to half dy. So after this, your probability the condition for normalization will be psi star psi h cross by m omega the whole raised to half into dy. Now we can substitute the values of psi and psi star in this equation to obtain integral minus infinity to infinity modulus of n square h cross by m omega the whole raised to half into h n square exponential minus y square dy equals 1. So this is your equation 15. Now, from the orthonormality properties of Harmonic polynomial, we know that integral minus infinity to infinity e raised to minus x square h n x h m x dx equals 2 raised to n factorial root pi delta mn. So using this condition, we can rewrite equation 15. This term will be a constant, can be taken outside, and this is very similar to this equation here, except that we haven't used we have already presumed that both m and n are the same, so it rules out the delta here. It will be 1 always. In that case, the equation will be n modulus square h cross by m omega the whole raised to half into pi raised to half, which is root pi, 2 raised to n into n factorial. Now the normalization condition demands that this should be equal to 1. So integral psi star d tau should be, or in the one-dimensional case, it's integral psi star dx. That should be 1. Now we can determine this normalization constant by rearranging the terms here. You will get nn equals m omega by h cross pi the whole raised to half into 1 by 2 raised to n factorial the whole raised to half. This is 16. Now you may substitute this in the equation for wave function, and you will get psi equals, instead of nn you must substitute m omega by h cross pi the whole raised to half, 1 by 2 raised to n factorial the whole raised to half into h and y exponential minus y square by 2. So this is your eigenvalue for the harmonic oscillator, and you know that when the first value, that is when n equals 0, h0y would be 1. Therefore your ground state wave function psi 0x equals m omega by h cross pi the whole raised to half exponential minus m omega x square by 2 h cubed. So this is the wave function on which, when the energy operator operates, gives you half h cross omega as energy eigenvalue. Now we have reached the last phase of our lecture, and we will have some discussions on the energy eigenvalues and eigenfunctions, and also a comparison between the classical and quantum harmonic oscillator will be done. So this is a plot which shows the probability and the wave function versus x graphs, and this parabolic curve here is your potential. This is parabolic curve because you have y or v equals half kx square as equation for the potential, and this is similar to y equals x square or y equals ax square, which is the simplest parabola. And you can see that these horizontal lines here represents the energies corresponding to n equals 0, the ground state, first excited, second and third excited states. If we plot this by giving the values of H, I think the values of H, the first few values of H are listed here, and you have to substitute H0 in here and put all n as 0 to get psi 0. And if you plot it against X, you will get a plot like this, a curve like this. And it is very important to see that this curve extends outside the potential barrier. Also, this is for n equals 1, and for n equals 1 we have h1 equals 2y. We have to substitute this in the equation for wave function, and in that case your wave function will be odd because it will be y an odd term into exponential term. And for n equals 2, h2 is 4y square minus 1, so your wave function will be even. So you will have alternate odd and even wave functions, just like what you got in the case of other simple exactly solvable problems like particle in a box, etc. So if you carefully notice, all these plots actually penetrates this barrier region here, which is not classically acceptable. But why is it? This is because of the peculiarity of the equation of wave function. To know more about this, that is how the wave function extends into the region beyond the potential barrier, I have a few data here. This is the stretching length, the length up to which your diatomic molecule, which is an example of a harmonic oscillator, stretch, and I have listed out a few values here. And this is your x, and this is your x square, which is the square of these values, and this is the effective mass of carbon stretching. We are considering CC stretching here, so this will be the effective mass of the system, and this will be the typical molecular frequency omega in hertz, and this is h cross. So towards this end, you can see this is the value of your eigenfunctions calculated. This is how it varies with x, and this is the value of the potential, and it varies with x. So if you notice, if you compare both these, you can see that their values vary by a significant margin, and it won't be easy to plot them on the same graph for a comparison. Therefore, we will have to scale the value. So we will be setting the maximum value of both these quantities as 1. Therefore, it will be easy for us to compare them. So I have done the scaling here for the wave function, and here the scaling is done for the potential. And after the scaling is done, I have plotted the graph. Let me see, it's here. Here is your graph. This is your potential, this is your potential, and this is your the wave function. And you can see that at this region it hasn't reached the 0 value yet. It still spreads out and exponentially decays. So this is how the wave function spreads outside the potential barrier region. If you look in this graph where the probability is plotted against x, you have definite probability of finding the particle outside the barrier. So it's a clear case of barrier penetration. Compare the ground state wave functions of a classical harmonic oscillator and quantum harmonic, not wave functions, probability of a classical and a quantum mechanical harmonic oscillator. You can see these dashed curves here, which actually traces the probability of of the classical harmonic oscillator, you can see that the classical harmonic oscillator is most likely to be seen at the extrema. See, a typical example is a simple pendulum with definitely the oscillation should be very weak if it has to be equated to the harmonic oscillator. So in that case, if you let the bob oscillate, then it will first reach the extrema where it will come to a halt. It will oscillate like this, and it will halt there, and then it will come back to its equilibrium position, right? Just like this. You have a bob suspended here, and you make it oscillate. It will oscillate up to here, up to a maximum point, and then it will. So at this point, what will be the kinetic energy? Kinetic energy will be zero because the bob comes to a halt here, and the kinetic energy will be a maximum here because as it moves down, this is a point where it will have maximum velocity. So it moves up here again, and the process goes on. So that's exactly the path drawn here, and you are more likely to see the bob here, the pendulum bob at the extrema, because that is where the bob slows down, and here the bob moves very quickly, and this is the point where it has the maximum velocity. Therefore, the probability of finding the bob here will be the smallest in the classical picture. So in the classical picture, your probability, C stands for classical, is proportional to the inverse of velocity. The probability of finding a particle is proportional to the inverse of velocity. Now if you look here, it's completely different. This solid filled curve, it gives you the probability density of or the probability value of your quantum harmonic oscillator. You can see that it is the maximum at the equilibrium position, say x equals 0. So the classical and quantum mechanical results contradicts here. So this is a main very important thing. So the classical concept that the probability of finding a particle is proportional to the inverse of velocity is not valid in the quantum mechanical world. Look at another plot. This is the case that we were discussing earlier, that is the ground state probability. Now if I plot for n equals 2, you will get 3 undulations like this, and you will have two peaks for n equals 1. In all these cases, it differs drastically from its classical analog. So now let's see what happens when n is increased. When n increases, this is the case of n equals 10, and when n is increased to a significant value, then we can notice that the classical and quantum mechanical picture almost overlaps, right? Here towards the extrema, this has the maximum value, and this curve almost traces the top of these peaks. And of course the quantum mechanical probability exhibit its undulating nature, and this simply means that the particle cannot assume any value. We will have a 0 here, a 0 here, a 0 here. At these points you won't be able to find your harmonic oscillator. And however, the classical mechanics results is different. Here you see a solid line, you have definite probability of finding the particle with anywhere here. Okay. Increasing n simply suggests that your harmonic oscillator can assume a lot of energy values. See, if n is very very high, say n approximately equal to 10,000, then you will have lines like this, very close lines, although they are separated. So this approaches the classical case, and when n becomes infinity, you will have the classical case itself, because you will have continuous energy levels where the harmonic oscillator can be seen. This is the classical concept. This is a transformation from the quantum mechanical to the classical world. So with that, we conclude our discussions on the quantum theory of harmonic oscillator using Schrodinger method. I request you to give me your comments and suggestions, and you can ask me any doubts you have. I think that I have covered almost every aspect related to the linear harmonic oscillator. Thank you.